Hi there, this is the second video for Chapter 8, Part 2, and this has to do with predicting products. Now, the last video covered reaction types, and hopefully you've gotten familiar with how to determine which type of reaction a particular equation is. If I give you a chemical equation, you can figure out which reaction type it is: synthesis, decomposition, combustion, single place, double placement. Now we're going to take it a step further, and I'm only going to give you this stuff on the left side of the arrow. I'm only going to give you the reactants, and you have to predict what the product. So you have to figure out what goes on the right side of the arrow. I give you what's on the left side of the arrow. You tell me what we're going to end up with on the right side of the arrow. And there's some steps we're going to work through here. The first thing is you want to determine which reaction type it is. And you should still be able to do that. Even though you have half the reaction, you still should be able to do that by looking at the pattern of the reactants. Now, once you figure out the reaction type, that will help you figure out what the products should be. And you'll see when we do some examples here. And a reminder, whenever we make a compound, just like when we were writing, going from words to symbols, when we were balancing those word equations last unit, whenever you write a compound, you do the switch trick. Whenever you have something alone, you check your list of diatomics, your 7 diatomics. And then you balance the equation. I will probably skip the balance the equation part of this just for the sake of time so I can get this video done as soon as possible. So we're just going to get into some examples here, and we'll come back to these notes up at top. So the first few examples here, let me get my screen over. What I'm going to do is I'm just going to write on the little screen over here the products. So the first thing I do, again, is I try and figure out, number one here, what is the reaction type? And if I look at it, I have what looks like a couple dancing and somebody alone. So it kind of looks like single replacement. But remember, you always want to make sure, if it looks like single replacement, make sure that it's not combustion. In this case, it is actually a combustion reaction. We have hydrocarbon plus oxygen. So when I see those two chemicals together, I see some sort of hydrocarbon. And the numbers don't matter. It could be C2H4, it could be C2H6, it could be C2H8, whatever. As long as it's carbon and hydrogen together, the numbers don't matter. And O2, oxygen, I know it is combustion. So what I'm going to do is I'm just going to put a C over here for combustion to remind me it is combustion. And once I know it's combustion, I know that from the last video, whenever we have combustion, we always make the same two things. We make CO2 plus H2O, carbon dioxide and water. So once you figure out its combustion, you can just automatically write CO2, H2O. Next example. We have hydrogen and chlorine. Notice hydrogen's all alone, chlorine's all alone. Well, picture them at JOH, two elements alone. They want to dance, so they do. So they come together. HCl. Now, little numbers like this 2 after the H and the 2 after the Cl never automatically come over to the other side of the arrow. The only time that the little number will come over to the other side of the arrow is if it's inside the parentheses. It's part of a polyatomic, and we'll probably see an example like that in a little bit. So you don't automatically carry over these little numbers. Now, what I did here is I made a compound. And just like I said up a second ago, whenever we make a compound, we have to do the switch trick. Well, if I look up hydrogen on the periodic table, it's a +1. If I look up chlorine, it's a -1. So in this case, they cancel each other out, so just HCl is my answer. Now again, I'm not going to balance this, but if I were to, I guess I will here, because it's an easy one, I'll put a 2 there. 2 H's, 2 Cl's, 2 H's, 2 Cl's on this side. So it's balanced. And again, that was synthesis. You can just write S if you want. I'll know what you mean. Just don't put SR because that's single replacement. So we have two simple things coming together to make a compound. Next one. This one, we have somebody alone and a dancing couple. So this is single replacement. And since it is a single replacement, we have a little extra work to do. The aluminums alone, barium and oxygen are dancing. So what I'm going to do here, get rid of this, and we're going to go up, look at our notes. There's a special set of instructions for single replacement reactions. It says, use your predicting products handout. I'll give that to you in class on Wednesday or Thursday. You can also print it off from the Moodle site. There's a link to it. You can print it off. Now, it looks like this. And notice there are kind of two columns here. The left column is for single replacement reactions. The right column is for double replacement reactions. So this was a single replacement, like we said a second ago. So we're going to use the left side. And what this is, it's a list of who the coolest cations, positive ions, and who the coolest anions are. So lithium is the coolest cation, positive ion, on the periodic table. It can, if it walks up to a couple dancing, it can kick anybody else on this list out. Potassium is the second coolest element. It can kick anybody out below it, but it can't kick out lithium. Barium, third coolest, so it can kick anybody out below it on the list, but it can't kick lithium or potassium out. So hopefully you see how that works. So that's a list for cations, positive ions. There's a smaller list of anions. As fluorine is the coolest, iodine is the least cool of the anions. And one of the rules we'll talk about here is cations will always replace cations. So if it's on this list, it can only replace things on this list. It's not like copper can try and replace chlorine because they're on different lists. It doesn't work that way. So what we have to do whenever we have a single replacement reaction is we check that list and we see if the reaction will happen. So if the element that has a higher activity that's higher on the list is already part of the compound, no reaction will occur. If the one that's alone is higher on the list, it will cut in and kick the other one out. So let's go back to that example. So we have aluminum, barium, and oxygen here. Aluminum's alone, barium and oxygen are dancing. So aluminum is going to come in and try and kick out either barium or oxygen. Now, one way I could look at this is I look at my list. Here's barium, here's aluminum, and they're on the same list. So the aluminum will try and kick out the barium. Another way of thinking of it is a metal will replace a metal, a non-metal will replace a non-metal. So in this case, the aluminum and the barium are our two metals. Now, if I can squeeze this all in here, oh, come on, there we go. If I look at my list, aluminum is right here, and barium is right here. Barium is cooler. So being that barium is cooler than aluminum, when aluminum comes up and tries to cut in here, barium's like, no, get out of here. Oxygen doesn't want to dance with you because I'm cooler than you. So what I would do in this case, since barium is cooler, aluminum can't replace it, all I'd do is I'd write no reaction, because nothing's going to happen. If I put aluminum and barium oxide in a container together, they just sit there and do nothing. So that is our first example of a single replacement. We'll have some more here, but let's move on to number 4. This, if you look at number 4, we see is a double replacement. Here we have two couples dancing. Aluminum and sulfate are dancing. Calcium and nitrate are dancing. So I'm going to need a couple things for this one. I'm going to need my polyatomic ion sheet. So if you don't have that, you want to get that out. You'll also want your periodic table because you'll need to do the charges because we're going to do the switch trick here eventually. So what I like to do is I just write the first one here, aluminum, And then what I do is I change the other one. So here aluminum is dancing with sulfate. So I know that on the other side of the arrow, aluminum is going to be dancing with nitrate. And now notice I automatically brought that 3 over to the other side of the arrow because it's in the parentheses. But I didn't bring this 2 over with the aluminum. I didn't bring this 2 over with the nitrate. I got to do the switch trick to figure those out. So what I usually do is I switch the second part of each dancing couple. So here the second part is sulfate, here the second part is nitrate. I switch those two things, and I leave the first things in the same order. So plus sign, I'm going to have calcium, and instead of calcium dancing with nitrate, I'm going to have calcium dancing with sulfate. Again, the 4 here in sulfate I brought over automatically because it's in the parentheses. Otherwise, I can't bring those little numbers over automatically. So I just made 2 new compounds, so I have to do the switch trick. If I look up on a periodic table, aluminum is a +3. If I look up on my polyatomic ion sheet, nitrate is a -1, and then I'll look up sulfate while I'm here too. Sulfate's -2. So nitrate I said is a -1. Calcium, if I look up on the periodic table, is a +2. And I just looked up sulfate, it's a -2. So in this case, with calcium and sulfate, +2, -2, they cancel each other out. So we can just leave it like that. Here, aluminum and nitrate don't cancel out. So I'm going to take that 3 and I'm going to put it outside the parentheses. Now, at this point, you could balance it. I'm not going to spend my time balancing it because I'm running low on time on this video. So I'll let you balance it on your own. But we do have a bit more work for the double replacements. And let me get this out of here real quick and go up. Now for double replacement, we're going to use the other half of that handout. And we only use it for double replacements, the other half. And we only use this handout for the replacements, single and double. All other reactions we assume will occur. So let me bring that up 1 second. Okay, so I have my predicting products handout here, and we are going to use this side, the double replacement side. Now it says, for a double replacement reaction to occur, at least one of the products must be a solid, a gas, or a covalent compound. In this case, the only covalent compound I'll give you is water. So if it makes water, we will have a reaction. If it makes a gas, we will have a reaction. I will tell you right now, none of the examples here are going to produce a gas, so you don't have to worry about that. It would be an obvious gas, like CO2, carbon dioxide, something like that. So basically what we're doing is we're trying to figure out if one of those things is a solid. Now, a couple definitions here. You'll need to know these terms, soluble and insoluble. And what I do here is I am going to look at my rules, and I'm going to find one of these rules that applies to these chemicals. So this first chemical on the right side in the products, I have aluminum nitrate. And I look here, oh, I have a rule for nitrates. It says all nitrates are soluble. And soluble means AQ. So what I can do is behind this chemical, I can put AQ. So for the next chemical, the next compound, calcium sulfate, I want to find a rule over here for calcium sulfate. And if I look and, oh, yep, I got one right here. It says all sulfates are soluble, except when the sulfate is with silver, lead, or something from group 2. And when by group 2, I mean the second column on the periodic table. And if you notice, calcium is in group 2. It's in the second column of the periodic table. So that's an exception. So sulfates are insoluble, and insoluble means solid. So what I'm going to do is I'm going to put a solid here. And I am out of time. So I will pick up here with the next video.